All right, let's solve this problem together. This one is from Hyunseo. We first need to check whether we have the left part or not. If we have left part, that means, right, so let's think about these two cases. If we have left part, that means this node is not the smallest one. However, if we do not have left part, left subtree, that means current node is the smallest node. So if that is the case, we are going to return the right subtree. So in this figure, if you do not have the left part, and if you just return the right subtree, then this node will be replaced with 11. So that is the case. And if we have the left part, that means we need to go to the left part. And we're going to update the left subtree by calling this remove first method on the left part. And then we're going to return self. So this is how we can implement this method. Okay? So this is the complete implementation of binary search tree. We initialize the binary search tree and we implemented the find method. And after developing this find method, we implemented find the smallest key in the subtree in the binary search tree and find the largest value in the given binary search tree. And we had to look at how we insert, create a new node or update, and how we remove a node in this binary search tree. So this was the complete implementation of binary search tree. And from now on, as I told you in the beginning of this class, we're going to implement a dictionary using binary search tree. So once we have binary search tree, implementing dictionary becomes very simple. We are going to first implement the constructor like this. And the root at first is none. And we're going to implement a find method. With the given key, we want to check whether we have the key inside our binary search tree or not. And because we are going to store a binary search tree in this root, we are going to call find key method here if we have self root. Otherwise, we are going to return none. Okay. And get item method becomes very simple. We just need to find the key like this. And if n is none, that means we do not have this key inside our binary search tree. In this case, we could erase like key error that we do not have this key inside this dictionary. Otherwise, we are going to return the value of that node. And we can also implement this contains method, whether this binary search tree contains a node with the given key. And what we are going to do is we just call this find method and check whether this one is not none. Okay. And sometimes we want to find the first key, that is the smallest key inside the dictionary. Then what we need to do is let's call the find first method. If we have self root, else we are going to return none. And last key is simple as first key. We're going to call the find last if we have self root. Otherwise, we're going to return none. And we can also implement this del item method, which will delete the key. If we have self.root, then we're going to update the root by removing the given key. So up to this point, we talked about how we can find some keys inside a dictionary or check whether this dictionary has a given key or not. And one of the most important things is how we can insert new items to this dictionary. That is, we're going to accomplish that goal through this set item method. We first need to check whether this root was initialized or not. If this one was not initialized, then we're going to initialize this one with a new node with a key and value. Otherwise, we're going to call this insert method to this root. So this is the implementation of a dictionary using binary search tree. So as you can see here, this is a wrapper class for binary search tree. Basically, we are using binary search tree as a dictionary. However, to improve the usability, we're just implementing a new class, dict. So that's all. And basically, we can just extend this binary search tree, this node class, to implement dictionary. However, we just want to separate the core part and the usage part, and that's why we are implementing this class dict separately. Okay. And so let's test our implementation a little bit. So we can create dictionary like this. And to this dictionary, because we implemented the set item method, we can insert these new items like this. And the key is going to be 7. This one will have keys 3. And GS 1401 like this. And we can print like this. And this print method prints the level. So 7 is at the zeroth level, and 3 is at the first level. So it is actually tree, binary tree, that looks like this. Okay. So this one visualizes this representation. And we can also update spring. The node with the given key 7 like this. So now D7 contains EC2202 spring, but before that it stored this one. So we can do this kind of things. And you can also test other functionalities on your own after class. And before I finish this class, I want to show you one problem of our implementation. Let's say we want to insert 100 numbers. like this. So what we are doing is we are inserting numbers to this dictionary from 1 to 100. Actually 99. And let's see what happens. If we do this, as you can see here, 1 is at level 0, 2 is at level 1, 3 is at level 2. So basically this binary search tree looks like 1 connected to 2, connected to 3. So basically this one looks like linked list. And we call this unbalanced binary search tree. And if this happens, all the other operations that we implemented, like find method or insert method, all the other methods, takes O n. However, if you have balanced binary search tree, then the time complexity is going to be log n. So this one does not change anything, even though we insert new items. It just finds the right place for the new node and insert it in the found position. Sorry for that. So this one becomes unbalanced once we insert items in order. So it becomes a problem. So we cannot make this operation very efficient. And in the next class, we are going to make our binary search tree balanced in all cases. Okay? So this is the end of today's lecture.